To the ancients, it was a god. To us, it is the powerhouse at the heart of the solar system, a blazing colossus generating heat and light and life, the sun. Its story begins over 5 billion years ago. A giant star is dying. It explodes as a supernova, the shockwave blasting through space toward a cloud of hydrogen. The cloud collapses, forming rings of gas and dust. At the core, a nuclear furnace fires up. Our sun is born. So too the 9 planets of the solar system. This empire of the sun is like a bubble. It's called the heliosphere. Within, the sun reigns supreme. Beyond is interstellar space. For the sun is a star, and as such, a beacon of energy. It heats and lights our world. All life depends upon it. The power we generate from fossil fuel is stored sunlight, energy that nurtured plants millions of years ago. So what is the sun, this local star of ours? Deep inside, at 15 million degrees Celsius, it's a nuclear reactor turning hydrogen into helium. Each second, the sun loses 4 million tons of mass, matter that's unleashed as energy. Slice open the sun, and we see the path of that energy. From the white-hot core, it takes 1 million years to reach the surface. It takes just 8.5 minutes for that same energy to speed the 150 million kilometers to planet Earth, energy we call sunlight. By analyzing its spectrum, especially the pattern of dark bands, astronomers discover the composition of the sun. It is 73% hydrogen, 24% helium, and a sprinkling of heavier elements. This is the solar surface, the yellow photosphere. Temperature almost 6,000 degrees, and above it, the fireworks of the red chromosphere. We look down on the photosphere, gas boiling up to the surface, cooler gas descending, each bubble the size of France. Not a sunflower, but a sunspot. Such blemishes periodically pockmark the sun. They're cooler than the surrounding photosphere. This one could swallow Earth. A group of sunspots. They can grow in 10 days, fade in 2 weeks. Here, the rotating sun has a spotty face. At other times, it's spotless. Sunspots indicate magnetic activity. They show where force lines burst from the sun and where they re-enter. The sun is like a garden sprinkler, swirling vast magnetic loops. Every 11 years, the magnetic poles flip. Midway between flips, the sun is at magnetic maximum, its force lines generated by gases just beneath the surface. The surface spins at different speeds. At the equator, it rotates once in 26 days. At the poles, it takes 37. This tangles and distorts the magnetic field. The result is a seething ocean of energy, our star unmasked. Within the chromosphere, the inner atmosphere of the Sun, arcs of gas sweep around magnetic force lines. Prominences leap into space, forming arches 50,000 kilometers high. Eruptions spew from the granulated surface. Prominences are surges of flaming gas triggered by magnetic releases deep below. These are major prominences, jets licking up to 100,000 kilometers. Tiny Earth is set into scale. But flares are more violent. They eject with the energy of 10 million hydrogen bombs. A flare blasts ripples across the solar face. The outer atmosphere of the Sun, the corona, is visible at a total eclipse when the Moon obscures the solar disk. The corona is hot, up to 2 million degrees, and it dances a magnetic jig. Convulsions on the solar surface shape the activity above. Great ejections from the corona are fueled by massive flares below. This ejection is so big that material speeds millions of kilometers to buffet the space probe SOHO. As the shockwave hits the craft, it is spattered with electrified solar particles. Such particles are continuously emitted by the Sun. They're the solar wind. Around the polar regions of Earth, the particles react with our upper atmosphere. They create the lights of the aurorae. The Sun has secrets, like what makes the corona so hot. At the solar core, it's 15 million degrees. At the surface, just 6,000. Yet out in the corona, it soars again to 2 million. The core's maybe magnetic energy. And we know the Sun throbs, but we're not sure why. Its deep oscillations are picked up by SOHO. They build a sound picture of the interior, and they reveal how the Sun changes shape. SOHO, which is operated jointly by America and Europe, is revealing more and more of what ticks beneath that churning exterior. It's discovered, for instance, that jet streams of gas whip through the Sun, the most powerful just beneath the surface. And there are tornadoes the size of Earth. They whirl near the poles at 500,000 kilometers an hour. "5 billion years from now, the Sun runs short of hydrogen. It starts to expand. From a diameter of 1.4 million kilometers, it bloats to 200 times that size, a red giant. The nearest planets vaporize: Mercury, Venus, Earth. Then begin the convulsions. Like cosmic smoke rings, the Sun puffs off a series of nebulae. The white-hot core is exposed. It collapses to the size of Earth, a white dwarf. Of the inner planets, only Mars survives in lonely orbit. Our Sun expires as a dead black dwarf. In the beginning, the solar system is a swirl of gas and dust. Little by little, it clumps together, smaller chunks of material plunging into larger aggregations. They form the planets. 4.5 billion years later, this is Mercury, closest planet to the Sun. Beyond Mercury, 3 more rocky little worlds: Venus, planet Earth, and Mars. Outward to the gassy giants of Jupiter and Saturn with its rings. Farther to the outer planets, Uranus, Neptune and Pluto, and to the icy debris of the Kuiper Belt. Here is the trash of the solar system, the comets of the Oort cloud, snowballs as old as the planets. For that's how the solar system shakes out. Mercury and the other inner planets condense from the heavier elements. Only the lightest make it to Jupiter and beyond. Condensing closest of all to the Sun, Mercury is rock solid. A clear evening on Earth. Mercury is on the right, Venus at the top. They skip through the sky close to the horizon. Tiny Mercury is the most difficult to see, barely clearing the skyline at dusk and dawn. Pull back from Earth and the reason is clear. We're seeing only part of their tight solar orbits. Venus, second from the Sun, takes 225 days to complete one orbit. Mercury, just 88. Occasionally, when it's aligned between Earth and the Sun, we see Mercury crossing the solar face. Outwardly, Mercury is like our moon, rocky, cratered, barren. But inside, like Earth, is an iron-rich core. That core is as big as the moon, and at 70% iron, Mercury is the densest planet of all. From the Sun, that searing pivot of the solar system, it's an average 58 million kilometers to Mercury. From Earth, it's much farther, and we've only once sent a space probe. November 1973, the Mariner 10 mission, liftoff to a planet uncomfortably close to the Sun. Such are the orbital configurations that it takes Mariner only 3 months to reach Venus. With the trick of gravity assist, Venus thrusts the craft onward to Mercury. First encounter is in March 1974. Mariner makes 3 flybys, and these are its pictures. Mercury is battle-scarred, scorched and irradiated by the nearby Sun, an ancient landscape of craters, cracks and basins. This is one side of Caloris, the site of an impact that gouged a multi-ringed basin 1,300 kilometers wide. The culprit is a planetesimal, a lump of primordial matter. Such missiles rained in torrents upon the early planets. A smack, 4 billion years old. Top right is Zola, a smaller impact, and here the pockmarks left by ejecta, material splashed from the crater. These craters are split by a huge fault. Mercury is riven with cracks, many of them the result of the Caloris impact. It may also have caused this lava plain, molten rock surging from beneath. But most plains post-date Caloris, they formed as cracks spewed great seas of lava. In contrast, Mercury's highlands have much sharper features. The epoch that created these plains runs for 1 billion years, but for the last 3 billion, there's been no volcanic activity. Mercury is inert, the interior solid. All that disrupts the surface are random whacks from space, calling cards like these. The arrow shows how slowly Mercury spins on its axis. It turns only 1.5 times in a single orbit of the Sun. The result is a crazy calendar. It means Mercury's day is twice as long as its year. The day lasts 176 Earth days, the year just 88. It gets stranger. If you stood on Mercury, you'd see the Sun apparently shrinking in the sky. It's to do with the variable distance of the Sun. For the planet has an elliptical orbit. The Sun appears larger when Mercury swings close, far away, and it's half the size. And there's a weirder effect. Each time it passes closest to the Sun, Mercury speeds up, then slows again. The result on the planet is a double sunrise. The proximity of the Sun means Mercury is hot. At midday on the equator, it can hit 430 degrees Celsius. The planet has a temperature range of 600 degrees, the greatest in the solar system. At midnight on the dark side, it can be as cold as -170. Even so, it's surprising that some astronomers believe there's ice on Mercury, ice permanently shielded from the scorch of the Sun. Radar mapping by telescopes in the United States and here in Puerto Rico indicate ice at both poles. If there is ice, it may have been left by comets, the ice preserved in perpetual shadow deep in polar craters. But confirmation must await a second mission to Mercury. Observations through big optical instruments are impossible. The planet is too close to the Sun. And who'd risk the eyesight of the Hubble Space Telescope? With a diameter of just under 5,000 kilometers, Mercury is the smallest of the inner planets. It has an atmosphere so rarefied as to barely exist, a magnetic field just 1% of Earth's. Almost all we know of Mercury is thanks to Mariner 10, a mission that left more than half the planet, the blank areas, still to be photographed. Venus, the veiled planet. Venus, choked in smog, a crushing atmosphere of carbon dioxide. Venus, shaped by volcanoes. Venus, where day and night it's always 480 degrees Celsius, yet no sun ever penetrates these poisonous skies. Venus is a puzzle. It rotates just once in 243 days, yet clouds race around the planet in 4. And with a diameter of more than 12,000 kilometers, Venus is almost the size of Earth, but few twins are so different. Once, Venus may have been like Earth, with oceans, continents, and clear blue skies. So what befell this unhappy world? What clouded its face? And why does it rotate backwards? From Earth, Venus is by far the brightest planet in the night sky, and like its elusive companion Mercury, best observed immediately after sunset and just before dawn. Neither climbs far above the horizon. It's the effect of their position between the Earth and the Sun. Mercury races around the Sun. Venus, farther out, takes longer, 225 days. It orbits at 108 million kilometers from the Sun. And occasionally, Venus crosses the face of the Sun. In 1769, the explorer Captain James Cook observes a transit of Venus that initiates the modern measurement of the universe. His observations from the Pacific are set against measurements taken elsewhere. By simple trigonometry, the latitude differential reveals the distance between Earth and the Sun. The unveiling of Venus begins with radar. It is the early 1960s and signals are bounced right through the Venusian clouds. Astronomers have their first image of the surface, and with it, the discovery that Venus rotates backwards. In 1966, and the Soviet Union starts sending landers through the clouds, the Venera missions. They detect an atmosphere 90 times denser than Earth's. Several craft are crushed. But a soft lander grabs these pictures. These are fractured slabs of lava. It seems Venus is massively volcanic. The images are beamed to Earth moments before the cameras frazzle. For machines don't survive here, much less human beings. If we ever reached the surface, we'd be instantly crushed. And to add to the horror, the upper clouds are bathed in sulfuric acid. Some Venera landing sites on this radar map. It shows a planet of plains, but few uplands. By contrast, our highlands on Earth form 7 continents. Venus has only 2. (1990), America's Magellan Mapper. Magellan turns this Venera imagery into this. Radar data come alive. We can see the surface and fly the planet. Venus rendered on computer. Heights are exaggerated and color guessed at, but otherwise the features are accurate. They're scanned by Magellan from orbit with radar for imaging and altimeter for heights. Three impact craters, rare on Venus because only the biggest space rocks make it to the surface. The rest vaporize in the super-dense atmosphere. Strip by strip, image by image, Magellan profiles the planet. Volcanoes with radiating lava flows. The Cleopatra crater, its rim breached by lava. Everywhere evidence of volcanic activity. Magellan confirms Venus as the most volcanic planet in the solar system. Volcanoes have belched here for possibly billions of years. No one knows why. And eruptions may still occur, their sulfur adding to the toxic atmosphere. Lava relays the surface time and time again. Many parts only solidify within the past $500 million years. And despite the volcanoes, Venus is remarkably flat, like an ocean bed smoothed by the motion of currents. Here, the Venusian winds have carried ash from a volcanic dome. These upwellings of lava seem squashed by the sheer weight of the atmosphere. Pancakes in a barrel of syrup. Overhead, the radar mission fulfilled, Magellan moves in for a new task, gravity mapping. It wobbles in its orbit because different densities of rock exert different gravitational pulls. In this way, Magellan analyzes the structure and composition of the subsurface. Deeper inside, Venus is rather like Earth. Same density, same crust, same mantle, same core. The core is solid, probably a mix of nickel and iron, but unlike Earth, there's no molten outer core, and as a result, the Venus of today has little or no magnetic field. October 1994, Magellan's career is over. It plunges kamikaze-like through the Venusian clouds. Mars, Earth and Venus mark out the habitable zone of the solar system. Venus, closer to the Sun, is at the zone's inner edge. But did it once have water, oceans and continents? Billions of years ago, it may have been this way. One theory is that the Sun, much closer and hotter than on Earth, slowly evaporates the seas. Water vapor fills the upper atmosphere. There it's split by the heat of the Sun. Hydrogen leaks into space. With carbon dioxide released from the oceans, the atmosphere thickens, heat can't escape. There's a runaway greenhouse effect. Venus is trapped in a giant pressure cooker. $150 million kilometers from the Sun is a beautiful blue world. This heavenly sapphire is our home, third planet from the Sun, the first with a moon. Earth with its abundance of water. We have oceans. We have an atmosphere laden with water vapor. We have ice. And where there's no water, desert. But where there is, an abundance of life. As far as we know, Earth is the only planet with life, and it is life that makes Earth so special. In the ferment of the early solar system, Earth has neither life nor water. It's a molten rock. 4.5 billion years later, and the heaviest elements have sunk to the center. The inner core is solid iron and nickel. Around it is the molten outer core. Around that, the mantle. This structure is revealed by seismic waves. Primary waves in yellow travel right through the core. Secondary waves in blue are blocked. Earth's magnetic field and its wandering north pole are caused by the solid inner core sloshing about in the molten outer core. If the poles reverse, as they've done before, it may be chaos for birds that navigate by magnetism. From below, hot magma pushes through the upper mantle to plume beneath the crust. The effect on the surface is continental drift. The evidence is beneath the waves, a mid-ocean ridge where molten rock is thrusting from the mantle to push apart the plates that carry the continents. Drain the oceans, and there are the plates, some pulling apart, others pushing together. Where plates meet, volcanoes spurt. Life is thought to have begun here, in ocean vents. On land, it evolves into green plants. They pump out oxygen. They convert our poisonous atmosphere into breathable air. As the toxic gases of our early atmosphere condense, rain starts to fall. Pools become lakes, lakes become oceans. Today they cover 70% of the planet. They lock up carbon dioxide, bequeathing us an atmosphere 1/5 oxygen, 4/5 nitrogen. And other forces are at work. By night, the stars seem to travel across the heavens, but it's an illusion. It's the effect of Earth spinning on its axis, a 24-hour rotation that gives us day and night. It's the same with the sun. As its shadow creeps across a dial, the sun isn't moving, it's the Earth. Day and night would always be the same length if the axis of our planet weren't tilted 23 degrees from the vertical. Add the complication of Earth's orbit around the sun, and the seasons are explained. An orbit takes a year. Each day, the angle at which sunlight falls on Earth changes slightly. Over a season, it's a lot. Over 6 months, the change is greatest of all. From this position, it's winter in the northern hemisphere, summer in the south. Short, cool days in the north, long, hot days in the south. 6 months later, when Earth is at the other side of the sun, it's summer in the northern hemisphere, winter in the south. Changing seasons mean changing sunsets. At the spring equinox in the northern hemisphere, sunset is due west. But by midsummer solstice, the sun comes from higher in the sky to set north of due west. At midwinter solstice, when the sun is lowest, it sets south of due west. And from satellite, here's the seasonal effect on ice cover. The oceans influence our climate. They pump currents around the globe, some hot, some cold. But fundamental to climate is the sun. At the equator, where it shines most directly, it causes hot, moist air to rise. This drives three great engines of air that circulate between the equator and the poles, air that rises and falls. It's the reason for our winds. If Earth didn't spin, they'd blow north and south. Since it does, they're slewed to the east or to the west. North Africa is cloudless because dry air is falling. To the north and south, moist air is rising. Flowing northeast across the Atlantic, the Gulf Stream carries warm Caribbean waters toward Europe. Lucky Europe, for the Gulf Stream delivers a mild oceanic climate to the northwestern seaboard. The weather is changeable but mild. Across the Atlantic, at the same latitude, winters are fierce. With no Gulf Stream, waterways freeze. When the ocean and the sun conspire, they create typhoons and hurricanes. These develop at sea from tropical storms, the sun heating vast quantities of moist air. The air spirals faster and faster with winds over 300 kilometers an hour. And if it hits land, from South America, a red finger of warm water extends across the Pacific. It's the work of El Niño. El Niño is a climatic tantrum. It occurs when there's a change in the pattern of trade winds. To the west, the ocean cools. To the east, it warms. There is far less rain in the west, more in the east. But the curse of El Niño reaches around the world. It's stormier along the eastern Pacific, right up to California. Indonesia is drier, and there are fires. Australia has drought. Our nearest neighbor. Our partner in space. So close that we land 12 men there and bring them safely home. The moon may be Earth's junior partner, but it pulls profoundly on us all. Sea turtles come ashore to lay eggs at new moon or full moon. Tides are highest and incubation best for the young. Not only does the moon influence biological cycles, but tides and timekeeping. By gradually slowing the spin of the planet, the moon has lengthened our day from 6 to 24 hours. Billions of years from now, the moon will make our day nearly 50 times as long. At more than 12,700 kilometers, Earth is nearly 4 times as wide as the Moon and 80 times as massive. Fly 10 times around our equator and you have the distance to the Moon. These are the phases of the Moon. They're a shadow effect caused because only half the Moon is lit by the Sun. Here it shines from the left. As the Moon makes its 27-day orbit, half the face is constantly illuminated. That's the perspective from space. But the amount of lit surface we see from Earth changes day by day like this. Though the Sun has some influence, ocean tides are mainly the work of the Moon. This time-lapse compresses just over 6 hours, the interval between low tide and high tide. The world over, twice a day, tides rise and fall as lunar gravity tugs on the oceans. They bulge at either side of the globe and are pulled ahead of the Moon because of the spin of the Earth. But tidal drag is slowing that spin. Simultaneously, Moon and Earth are pulling apart. Ultimately, our planet will spin only once every 47 days. And Mother Earth is subject to another tug of her satellite. It makes her axis wobble. The cycle lasts nearly 26,000 years. It means the pole star of today won't be tomorrow. A ring of debris orbits our red-hot proto-Earth after the impact of a planetesimal nearly half our size. This collision is thought to have formed the Moon. It solidifies from crust and mantle splashed up from the planet and from the projectiles that buzz the early solar system. Our infant Moon. 4.5 billion years later, it still bears the scars of those impacts, the dark regions, the so-called seas of the Moon. They look that way because the interior of the young Moon is still liquid, like the contents of an egg. So when the crust is punctured by a space rock, the resulting basin fills with lava welling from beneath. It solidifies into a mare, a sea of dark rock. Such upwellings ceased just over 3 billion years ago as the interior hardened. This is the surface of today. Uneroded by wind or water and bare of vegetation, it is a stark record of impact after impact after impact. All that erodes old craters are new craters. There are craters within craters. This one, 90 kilometers wide, is pockmarked with later impacts. A smack like a pebble in mud. This is the ray crater Tycho. Compared to much older craters blackened by the sun, ray craters are bright and young. They're caused by the splash of an impact and are the brightest features on the face of the Moon. The Alpine Valley. Not a valley at all, but a great fault cutting through the lunar Alps. Smaller clefts are called rills, and they're possibly ancient lava channels. Here the contrast of smooth mare and rugged highlands. We fly toward the Alps and over the dark crater Plato. But this is a desolate place, barren, airless and lifeless. By day, temperatures rise to 120 degrees Celsius. At night, they fall to minus 160. And gravity is just 1/6 of Earth's. In 1969, astronauts Buzz Aldrin, Neil Armstrong and Michael Collins head for the moon. The Apollo 11 mission. Three and a half days later, Armstrong and Aldrin descend from lunar orbit in their landing module Eagle. Armstrong skims the craters in search of a safe landing. They make history.
We copy you down, Eagle. It's one small step for man, one giant leap for mankind. It's one small step. It's one small step. It's one small step. One giant leap for mankind. One giant.
There are 6 Apollo landings, incredible achievements.
One giant leap. It's one small.
But they are more to do with flags and footprints than with science.
We copy you down, Eagle.
But at the end of each mission, after rejoining the command craft, the lander is crashed back to the surface. The impacts ring the moon like a bell, indicating pulverized rock immediately below the surface, rock that reverberates. But the moon is solid, its core metallic. The astronauts return more than 380 kilos of rock to Earth. The samples are either volcanic or the product of impacts. (1998) and the Lunar Prospector mission. Prompted by these geological maps from an earlier survey, the hunt is on for lunar ice. This image hinted at the possibility. The circle is the Aitken Basin, a huge depression at the South Pole. Prospector's sensors verify the hunch. Aitken has millions of tons of water, but deep frozen and locked up in rock. It's the same story at the North Pole. The last astronauts left the moon in 1972. With water confirmed, they'll be back. The sun is the light of our lives, radiating with the power of 400 trillion watts. Each second, it converts 4 million tons of mass to searing energy. It emits heat and light, everything from X-rays to radio. But as hydrogen is converted into helium, and as gas flares into space, a less tangible emission blows from the sun. The solar wind, a continuous stream of electrified particles. They take up to 4 days to reach Earth, but they don't touch the planet. We're protected by our magnetic field, the magnetosphere, a great bubble that deflects the solar wind like the bow wave of a ship. Normally, the wind blows at up to 400 kilometers a second. But massive solar ejections like these can boost it to storm force, to 800 kilometers a second. On Earth, they cause geomagnetic storms, knocking out power lines, blacking out cities. And they can send satellites into a spin. When India lost a communications satellite, the stock exchange shut down. Mass ejections from the sun are infrequent, but here, with the solar disk masked, there's no mistaking their power. As an ejection hits us, the magnetosphere is squeezed. We suffer a geomagnetic storm. Between these major eruptions, the sun emits a steadier stream of electrified particles. They get near Earth only around the poles, where magnetic force lines funnel them toward the planet. The result is the lights of the aurora. From satellite, this is the aurora borealis, an oval of electrified particles reacting with our upper atmosphere. The aurora borealis circles the northern polar regions. Toward the South Pole, it's the aurora australis. From ground level, it's the stuff of dreams. We're watching the effect of electrified particles spiraling down magnetic force lines. They're colliding with atoms and molecules of oxygen and nitrogen. As their intensity changes, so does the color. The aurora. Every so often, when planet Earth lines up with the Moon, we enjoy another celestial spectacular. Since ancient times, these shows have beguiled us, for the main player in the alignment is that light of our lives, the sun. It's the blocking of sunlight in an alignment that causes an eclipse. The intervening body, in this case the Earth, casts a shadow. To understand the mechanics of an eclipse, we start with an eclipse of the Moon. The Moon's orbit around Earth is inclined by 5 degrees to the horizontal, to the ecliptic. In each 27-day orbit, the Moon twice intersects the ecliptic, points we know as nodes. Here. And here, with the sun shining from lower screen, an eclipse occurs only when Earth and Moon align at a node. A lunar eclipse, and a solar eclipse. With the sun shining from the left, the Moon moves into the shadow cone of Earth, here in white. The result is a total lunar eclipse. The Moon goes red. The cause is Earth's atmosphere. At totality, it bends and filters sunlight to project a red blush. Now, an eclipse of the Sun. But because the Moon's orbit is slightly elliptical, this eclipse isn't total. The Moon is at its farthest from Earth, and the shadow cone doesn't quite reach us. So from Earth we see an annular eclipse. The Moon's too far away to completely cover the Sun. That's always the case on Mars, where the tiny moon Phobos gets nowhere near a total eclipse. This one does. The moon is close enough for its shadow cone to sweep the Earth. Here's the shadow of the August 1999 eclipse racing across Europe toward the Black Sea. From satellite, another shadow path. At its slowest, the shadow cone travels across Earth's surface at the speed of Concorde, 2,000 kilometers an hour. But it can go 3 times as fast. In 1998, it scoots across the southern Caribbean as Earth, Moon and Sun align. The island of Curacao, enthusiasts from around the world assemble for a total eclipse of the sun. Cameras, telescopes and binoculars are fitted with special filters. It's the only way to safely observe the sun. First contact.
Look at the sky.
But as the moon edges across the solar disk, clouds threaten the show. Conditions clear, this partial phase lasts an hour and a half. Binoculars project a twin image of the crescent sun. Totality approaches. The sun is totally eclipsed by the moon. Quickly, off with the filters. For 3.5 magical minutes we can see the corona, the outer atmosphere of the sun. The moon exactly covers the solar disk. It's 400 times smaller than the sun, yet 400 times closer to us. And there, with the eclipse, the planets Mercury and Jupiter. The diamond ring, and totality is over. Sun up on Mars, the dusty red planet. Mars is fascinating, for it's the world on which next we'll tread. It's little over half the size of Earth, but there's much in common. Mars has an atmosphere, seasons, and a day of 24.5 hours. But the red planet is bitterly cold, at best just above freezing. The sun is at an average distance of 228 million kilometers. One solar orbit takes 687 days. Mars setting behind one of its 2 tiny moons. They're probably ancient asteroids, petrified rocks captured by an ice-cool planet. Like Earth, Mars has a tilted axis. That and its elliptical orbit distort the seasons. Farthest from the sun, it's summer in the northern hemisphere and winter in the south. Closest to the sun, and it's winter in the north and summer in the south. At the North Pole, the ice cap grows in the short, relatively mild northern winter. It shrinks in the long, relatively cool northern summer. At the other pole, the southern ice cap grows much bigger. Compared to the north, winter in the south is long and severe. But the southern summer is short and less cool than summer in the north. Geologically, Mars has a divide. To the south, older cratered terrain. To the north, younger lava plains. The first close-ups are from the 1960s. They're flybys of the early Mariner missions. This picture of dark spots in a dust storm is clarified later as 4 huge volcanic peaks. For when dust storms kick up on Mars, they can last for weeks and envelop the planet. In 1976, orbiters called Viking revolutionized our understanding of Mars. They hint at subsurface ice. Did the impact that gouged this crater spill melt ice over the rim? As this flood channel testifies, water once flowed on Mars, an ancient island. The Vikings photographed frost and early morning fog. And the notorious face on Mars, just a trick of light. (1976), the Viking landers. 2 robots dig for signs of Martian life. But nothing stirs. For an idea of scale, superimpose North America on Mars. The distance from coast to coast is some 4,000 kilometers. That's the length of the red planet's greatest rift, Mariner Valley. We take a second look, but from closer to the surface. Skimming the craters of the southern hemisphere, we turn west to fly the largest geological fault in the solar system, Mariner Valley. To the highlands west of Mariner and the volcanic dome of Arsia. Another called Pavonis. A third named Ascrius. But this is the volcanic peak that tops them all, Olympus Mons. Rising 27 kilometers, Olympus Mons is 3 times the height of Mount Everest. These cliffs alone are 6 kilometers high. Olympus Mons is the biggest volcanic peak in the solar system. There's a theory of oceans forming on early Mars because of immense volcanic upheaval. Eruptions melt subsurface ice, quickly flooding the planet. A respectable atmosphere develops of carbon dioxide. Temperatures soar. So why doesn't Mars go green and spark life? One factor could be climatic instability caused by huge variations in the tilt of the planet. But the main reason is volcanic shutdown. No major eruptions to replenish the atmosphere. An atmosphere slowly leaking into space because of weak Martian gravity. Mars Pathfinder, In 1997, it sets down on an old flash flood plain. It trundles out a robot rover to analyze the composition of the rocks, with intriguing results. Apparently carried on great surges of water, the rocks are quite diverse. Some are volcanic, similar to those formed in oceans on Earth. Was this once a floodbed leading to a Martian ocean? Supporting evidence from orbit with the Mars Global Surveyor. Charged with mapping the planet in unprecedented detail, Surveyor scans a huge flat region in the northern hemisphere. It has all the characteristics of an ocean floor. By contrast to that watery epoch, today's Mars is a freezing desert, retaining not a drop of liquid water. But Mars does have the vestige of a magnetic field. It's measured by Global Surveyor. Destination Mars. With the success of Pathfinder and Global Surveyor, regular twin missions are planned, each with a lander and an orbiter. Known as the Mars Surveyor program, the objective is to understand the story of water on the planet. Many scientists believe it abounds there, locked up as ice beneath the surface. The orbiter is to trace flood channels and in false color map the geology. Meanwhile, the lander streaks through the Martian atmosphere, 150 times thinner than our air on Earth. On the surface, it continues the hunt for life. Could microbes survive here, bereft of warmth and water? And could we? Is this dusty world a place for human beings? Only time and the robots will tell. Supernova, death of a giant. The entrails of a star up to 100 times the mass of the Sun splatter across space. But out of catastrophe comes regeneration. From the debris, new stars are born. They fire up in regions like this, clouds of gas and dust, nebulae enriched by the supernova. For the blast carries metals like iron and gold, heavy elements spawned only in the most massive stars. Thus does a supernova seed its offspring. In this birth, a cloud of debris collapses under its own gravity. It forms a disk. At the center, a star begins to shine. Around it, rings emerge, rings that resolve into planets. Our solar system evolves this way. Earth orbits comfortably in the blue habitable zone, where life is possible. A rain of comets brings us water. Lightning is possibly the catalyst for life. Our early atmosphere is thick with carbon dioxide. But Earth is a beneficiary of that supernova. We're rich in phosphorus and sulfur, elements essential to living cells. As those cells evolve into higher life forms, green plants breathe oxygen into the air. Earth becomes the perfect incubator for life, neither too hot nor too cold. We're at just the right distance from the sun. The same can't be said of Mars. It's a freeze-dried desert where, even on the warmest days, temperatures barely top zero. For Mars lies just beyond the habitable zone. Yet, less than a century ago, some astronomers believed in Martians, a civilization that dug a network of canals to carry water from the poles. Alas, those imaginary channels never irrigated a green planet. But Mars may once have had oceans and just possibly microbial life. The oceans disappeared, it's thought, because Mars is so small. Weak gravity allowed the atmosphere to leak into space. Stripped of its warming effect, the red planet froze. Today, the polar caps are a visible remnant. But many scientists believe vast reservoirs of water lie frozen beneath the surface. And who knows, microbes may survive there, or at least a fossil or two. But if we find new life in the solar system, it's most likely to be here. This is the extraordinary surface of Europa, a satellite of Jupiter. A little smaller than our moon, Europa is entirely covered in water ice. It may be tens of kilometers thick. This pack ice on Earth looks remarkably similar. And beneath it lies an ocean. If Europa's the same, great seas may wash under the icy crust. And they could be warm, heated by volcanic activity. As in oceans on Earth, hot vents may support primitive life, organisms that feed on chemical rather than solar energy. Europa must be explored. Onward and outward. We're now so far from the heat of the sun that no life could possibly exist. We've reached Saturn, where the temperature of its cloud tops is minus 180 degrees Celsius. But the gas giant isn't our quest. We're headed for Saturn's largest moon, Titan. Titan is a laboratory for the origin of life. With a surface temperature of minus 200, it's an unlikely place. But Titan's cloudy atmosphere has lots of hydrocarbons. They react with ultraviolet light from the sun. Photochemical reactions produce organic molecules. Such carbon-based compounds are the first stage in the generation of life. But Titan's too cold to go the next step. Titan is like Earth in deep freeze. The atmosphere, like ours, is rich in nitrogen. It contains water molecules, here in blue, a legacy of comets. The ingredients of early Earth are present. To come alive, all they need is heat. They'll get it 5 billion years hence, when the sun swells into a blazing red giant. Since 1983, this dish has listened out for extraterrestrials beyond the solar system. We've sent messages with the Pioneer and Voyager spacecraft, but from the stars, there's been not a peep. Nevertheless, evidence mounts that other stars have planets. Among them surely must be an Earth-like world. Such planet-forming stars are born in nebulae like this, clouds of gas and dust that pervade our galaxy. The excitement for astronomers is that these clouds contain the building blocks of life. They have water and organic molecules. As a star forms at the heart of a collapsing cloud, so the disk that emerges spins its center clear of debris. That debris makes planets. Here's a real star with a protoplanetary disk. And another, both pictured by the Hubble Space Telescope. This animation is of the star Beta Pictoris. In the clear center of its disk, a planet orbits. We may not be able to see a planet, but we know it's there because its gravity tugs on the star. The star wobbles. Astronomers detect the wobble by means of the Doppler shift. The star is blue as it moves towards us, red as it goes away. This Hubble image is a puzzle. It shows a pair of stars that have apparently ejected a planet. A trail leads us to it. Is this the first direct view of a planet outside our solar system? This one isn't a planet, it's a brown dwarf, with up to 50 times the mass of Jupiter, but too small to be a star. So far, of stars discovered to have a planet, none could support life. This planet has too close an orbit. The problem with this one is too distant an orbit. But when we do find an Earth-like planet, it's bound to be weirder than we ever guessed. Between Mars and Jupiter, a belt of asteroids have their orbits, rocky remnants from the birth of the solar system. They live quiet lives, but accidents happen. Collision or a jolt from Jupiter's gravity, and an asteroid is knocked from its orbit. Drawn inward by solar gravity and with a nudge from Mars, this space mountain is now a projectile. It's 65 million years ago. 10 kilometers of rock and metal are on a collision course with Earth. Doomsday for the dinosaurs. Earth suffers a cosmic winter and mass extinction. A much bigger impact 4.5 billion years earlier gives us the Moon. Earth is struck by a planetesimal the size of Mars. Debris splashed into space either returns to Earth or clumps together to form the Moon. It's good news, for the Moon slows our planet's spin and accelerates the evolution of life. By contrast, the Moon is lifeless and barren. No oceans, nothing hides its scars. Peer through a telescope, and scars there are. 30,000 craters pockmark the surface. Each depression testament to an impact. Uneroded by wind or water, a pristine record of wax from space. Per square kilometer, Earth takes as many hits. Strip away our atmosphere, our seas, our vegetation, and all geological movement, and this would be our planet. Impactors reach planets even today. Jupiter, 1994. The culprit is this string of pearls. Discovered 2 years earlier, they're fragments of the same comet, Shoemaker-Levy 9. Straying too close, Jupiter's Herculean gravity rips the comet into more than 20 pieces, like dust sucked into a vacuum cleaner. The fragments now hurtle for the giant planet at 60 kilometers a second. Were it not for Jupiter's pulling power, far more comets would get through to Earth. Imagine these bruises on our tiny planet. The plume of an impact outshining the aurora. The shockwave of an impact. It's as big as Earth. Picture the consequences had those crags hit us. (1972), and this space rock almost does. 80 meters wide and moving at 10 kilometers a second, it could destroy a city. Luckily, it skips off the upper atmosphere and back into space. 1992, high school football on America's East Coast. A fireball stops play. The missile breaks up, and some chunks are recovered as meteorites, the name for any cosmic debris that makes it to the ground. Siberia 1908, this projectile, 60 meters wide, doesn't reach the ground. It explodes in the atmosphere like a nuclear bomb. Over 2,000 square kilometers of uninhabited forest is flattened. Had this happened over London, millions would be dead. The asteroid belt is like an orbital motorway. Those that stick to the road are fine. Those that veer off threaten us. At least 100,000 asteroids cross the orbit of Earth. 2,000 are big enough to cause us problems. Robots are sent to assess them. This one is to rendezvous with the asteroid Eros. In its current orbit, Eros is harmless. But in 100,000 years, it may well be on target for Earth. We must make its acquaintance. Eros is 40 kilometers across, 4 times the size of the missile that slew the dinosaurs. If we're still around and we don't stop it, nobody, no life on Earth, will survive this rock. In 1999, a probe investigates another threatening asteroid. Currently in a Mars-crossing orbit, a gravitational twitch could send it our way. The probe is to report. This craft, Rosetta, is scheduled for a closer encounter. Launching in 2003, it's to fly by 2 asteroids and waltz with the comet Vertinen. A lander is to analyze the nucleus. Earth space buzzes with eccentric comets and Earth-crossing asteroids. For every one plotted here, 20 or more are yet to be discovered, some posing the threat of global extinction. But we, unlike the dinosaurs, can react. We can build a parabolic mirror and tow it into space. There it concentrates reflected sunlight on an Earth-threatening missile and scorches it off course. Another concept, giant pods close with an enemy asteroid and attach to its surface. They release super sails that catch the solar wind and tug the intruder away. Or how about this device? Like a celestial outboard motor, it shunts the object to a safer course. But suppose there's too little warning. A space rock will hit us in weeks. Do we go for the nuclear option? Crude, simple, a last resort, a direct strike, and who can predict whether it would save the world? Given the political will, an international search program could hunt down most of the comets and asteroids that threaten Earth. With advance warning, defenses could be mobilized. But there is still the nightmare scenario. At the edge of the solar system, in the icy depths of the Oort cloud, the gravitational hiccup of a nearby star perturbs a comet. It begins a million-year journey toward the sun. "90% of our skies go unchecked for intruders. The comet takes us by surprise. "10 kilometers wide, velocity 20 kilometers a second. It's as big as the dinosaur killer. Armageddon. Extinction. A 100 million megaton explosion vaporizes New York City. The crater is 200 kilometers wide. A shockwave blasts outward, flattening everything in its path. It'll travel around the globe as a cosmic winter descends. The reign of humankind is over. Jupiter is a giant ball of gas, bigger than all the other planets put together. Jupiter spins like a top. It has the shortest day of any planet, turning once on its axis in less than 10 hours. Glimmering through Jupiter's ring of dust, the Sun is but a beacon 780 million kilometers distant. So remote that it takes Jupiter nearly 12 years to orbit the Sun. Jupiter dwarfs our planet. It needs 11 Earths to span Jupiter's diameter, and over 1,300 to fill its volume. Where comets are concerned, Jupiter is like a vacuum cleaner. This comet, on a journey from the fringes of the solar system, swings a little too close. It's captured by Jupiter's gravity. Subject to forces hundreds of times greater than the pull of the moon on the ocean tides of Earth, the comet fragments. It's July 1994, and more than 20 pieces of comet Shoemaker-Levy 9 plunge towards Jupiter. In 1977, from our little blue planet, twin space probes head for the outer solar system. They're the Voyager missions, whose first target is Jupiter. 2 years later, the planet fills their sights. It's like no other. There's no surface, no solid features, just gas. whirling in gigantic belts of weather. The belts blow in opposite directions, eddies and storms racing round the planet. The biggest is the Great Red Spot, a tempest 3 times the size of Earth, an anticyclone that's raged for centuries. At the top, the red spot from Voyager 1, below from Voyager 2. Ten years later, from Earth orbit, Space Shuttle launches Galileo. By way of Venus and twice past Earth, it's 6 long years to Jupiter. Galileo makes it. In 1995, a probe is deployed for a descent into hell. The plunge is slowed by parachute. Every second is vital for research. The clouds thicken. Winds blow at 500 kilometers an hour, driven by Jupiter's heat. Temperatures soar. Jupiter generates far more heat than it receives from the sun. The core is 30,000 degrees Celsius. 40 minutes in, and the atmosphere is 10 times denser than Earth's. 1 hour in, and the Galileo probe expires, crushed by pressure. Jupiter is 90% hydrogen, the rest mainly helium. Haze tops the atmosphere. Then crystals of ammonia, ammonium hydrosulfide, water ice, and droplets of water and ammonia. Deeper to hydrogen and helium, liquid hydrogen, metallic hydrogen, and a rocky core. It's that liquid metallic hydrogen that generates Jupiter's magnetic field. This donut-shaped zone buzzes with electrified particles. But Jupiter's magnetosphere stretches much farther. After the Sun, it's the biggest entity in the solar system. And where the solar wind funnels toward the planet, auroral halos display around the poles as charged particles interact with the upper atmosphere. The 16 moons of Jupiter. Galileo, after launching its probe into Jupiter's clouds, has business with these satellites. First to Io, a moon flexed by the tug of Jupiter and the pull of a neighboring moon. The result is erupting volcanoes, first pictured by Voyager. Io is the most volcanically active body in the solar system. It heaves with eruptions. Lava relays the surface over and over again. Plumes feed the sulfurous atmosphere. By contrast, this moon is placid, Ganymede. At minus 150 degrees, the icy crust is 100 kilometers thick. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury. Around Ganymede, Galileo detects a weak magnetic field. It hints at the internal structure. Beneath the crust, a mantle of slush. Then a layer of rock and ice surrounding a silicate core. Almost Ganymede's double is this moon, Callisto, except for the craters. They record eons of bombardment, the greatest impact site, a vast ringed basin. And here's another imaged by Galileo. If there's extraterrestrial life in the solar system, it could be here, on Europa. Smooth and cracked like an eggshell, there's a theory that the whole moon is an ice-covered ocean, a possible medium for life. For the waters may be warm, heated by gravitational flexing caused by Ganymede and Io. But this ice may be many kilometers thick. To penetrate the ocean and search for organisms must await a landing. Nevertheless, the grooves and fissures that network the surface are cause for hope. They're reminiscent of frozen oceans on Earth, and what life teems beneath their ice. The Big Four of Jupiter's 16 moons, a mini solar system. Liftoff for Cassini, last of the big spenders. It's 1997. And 5.5 tons of spacecraft head for Saturn. Cassini reaches this exotic giant in 2004. The mission costs $1 billion. So what prompts this costly and lengthy undertaking? Our world is just 150 million kilometers from the sun. Sweep out past Mars, last of the terrestrial planets, and cross the Great Divide to Jupiter. Saturn is beyond. This beautiful planet is nearly 10 times farther from the Sun than is Earth. Its solar orbit takes almost 30 years. Its daily rotation, 10.25 hours. After Jupiter, Saturn is the largest planet, so buoyant that in an ocean big enough, Saturn would float. Yet it could swallow Earth nearly 750 times. Like Jupiter, Saturn is gas, 94% hydrogen, the rest mainly helium. And it has similar weather bands, but haze makes them hard to see. They're revealed by changing camera filter, full of storms and eddies. Winds are faster than on Jupiter. This jet stream blows at 1,500 kilometers an hour. Saturn's atmosphere has 5 layers, with haze at the top, then crystals of ammonia ice, ammonium hydrosulfide, water ice, and water droplets. Deeper still to hydrogen and helium, then liquid hydrogen, metallic hydrogen, and a rocky core. As with Jupiter, it's the metallic hydrogen that generates Saturn's magnetic field. It diverts the solar wind, except where electrified particles funnel toward the poles. They generate aurorae. Watch the North Pole. From afar, the rings of Saturn are like gossamer. Close to, there are billions of moonlets, from specks of dust to icy rocks the size of trucks. On a scale we can appreciate nearer home, the rings stretch so wide that they'd fit between our planet and the orbit of the moon. But they're no more than a kilometer thick. From Earth, our view of the rings changes as Saturn orbits the Sun. It's because of the tilt of the axis, 26 degrees. Edge on, the rings virtually disappear. Our knowledge of the rings is through the Voyager flybys of the early 80s. They reveal 7 main bands, each with hundreds of ringlets. And they record time-lapse of mystery spokes, possibly dust levitated above the rings by electrostatic forces. With a background star as reference, Voyager catalogues the rings and their divisions. This largest gap is the Cassini division, 4,000 kilometers wide. Some of the rings are kept neatly in orbit by little shepherd moons. Here's a pair marshalling the outermost ring. This moon, called Pan, orbits within the Encke division. But the rings are a puzzle. They may be the debris of pulverized space rocks, too close to the planet to clump together as moons. Within a few million years, the rings of Saturn may well disperse. Voyager time-lapse of Saturn and its moons. There are 18 known satellites. Tiny Mimas is one of the oddest, ice and rock and a gigantic crater. Had the projectile that caused it been bigger, Mimas might be a Saturnian ring. Enceladus, nearly twice the size, but still just 500 kilometers across. Plains of ice formed perhaps as water welled up from beneath. Icy fountains may still spurt here as Enceladus is flexed by the pull of its neighbors. Next in Voyager's sights, Tethys, over 1,000 kilometers across, and a great canyon just visible at the underside. Dione is similar, but with one hemisphere brighter than the other. An icy surface of craters and troughs. A close-up of Rhea, a big moon 1,500 kilometers wide. Iapetus has one hemisphere coal black, the other snow white. Tiny Hyperion is like a distressed hamburger. And this little rock periodically swaps orbits with a twin. Saturn's biggest moon, larger than the planet Mercury, is discovered by telescope in 1655 by the Dutch astronomer Huygens. The moon is Titan, and it's a little like early Earth in deep freeze. Titan is veiled in haze, but Voyager senses the presence of organic molecules, carbon-based compounds like those that sparked life on Earth. We can only guess at the surface, for Voyager sees nothing through the all-enveloping smog. Hail Cassini. On its arrival in 2004, Cassini deploys a lander, appropriately named Huygens. The descent takes 2.5 hours. The atmosphere is rich in nitrogen, just like Earth. Data is flashed to the mother craft and onward to Earth. On landing, Huygens has just 30 minutes of life. Temperature is minus 190 Celsius. There's no sun for solar cells, and it's snowing ethane and methane. Titan may have oceans of hydrocarbons, but Huygens can also handle a splashdown. Again, only half an hour to signal Earth with those vital clues. Is Titan a laboratory for life? That's reason enough for this billion-dollar mission to the Lord of the Rings. Seventh planet from the Sun and orbiting on a strangely tilted axis, Uranus inhabits the twilight zone. Uranus is a gas giant with rings and moons. This one, Miranda, is the rough diamond of the solar system, a rocky little ice chip with cliffs taller than Mount Everest. It's cold out here. Uranus is 19 times farther from the Sun than is planet Earth. In 1977, a star winks as it passes behind the planet. The winks reveal the rings of Uranus. Astronomers count 9. Subsequently, 11 are confirmed. They emphasize the severe tilt of the planet, all of 98 degrees. Uranus orbits on its side. With a diameter of over 51,000 kilometers, it's far larger than Earth. But compared to Jupiter, that's modest. Uranus may be a giant, but Jupiter is a supergiant. In 1986, and from Voyager, the first close-up. An apparently featureless ball. With infrared, the Hubble Space Telescope sees a little deeper. It spies 3 hazy layers of atmosphere. There may be weather down there, but it's obscured. The moving arrow shows the odd angle of the magnetic field through Uranus. Compared to the rotational axis, the magnetic axis is offset by 60 degrees. On Earth, it's only 11. The atmosphere is mainly hydrogen with helium and a touch of methane. The upper band is a narrow layer of haze rich in hydrocarbons. Below, hydrogen and methane, then ammonia and hydrogen sulfide, and a transition zone of gas and liquid. Deeper still, liquid hydrogen. A mantle of ices, and a rocky core. Uranus has 17 known moons. One of them, Miranda, is shattered early in its life. Some of the debris forms the rings of Uranus. The rest reassembles into Miranda Mark II. That's the theory. It's unproven, but it does explain the rings. Or perhaps Uranus is struck by a body the size of Earth. That could account for both the icy rings and the tilted axis. Either way, the chaotic contours of Miranda are like a moon reconstructed. Miranda, less than 500 kilometers across, is a riot of geological form. The most spectacular, these ice cliffs up to 15 kilometers high. Fall from the top in this puny gravity, it would be 14.5 minutes before you hit the ground. This moon, by comparison, is dull. It is aerial, more than twice the size of Miranda, a network of canyons, faults and frost. Umbriel, a little bigger, has an ancient surface pockmarked with craters. Titania has a canyon to rival Africa's Rift Valley. It's the largest moon, 1,600 kilometers across. Finally, Oberon, outermost of the big moons. Uranus, where a day is almost 18 hours and an orbit of the Sun takes 84 years. We've reached Neptune, last of the gas giants, last major planet. So remote that when it's surveyed by Voyager in 1989, radio data takes 4 hours to reach Earth. Neptune's solar orbit takes 165 years. This planet is 4.5 billion kilometers from the Sun. Problems in predicting the position of Uranus lead to the discovery of Neptune in 1846. Most of the time, Uranus is either ahead of or behind its calculated position. Something is perturbing its orbit. That something is Neptune. As Uranus on the inner orbit catches up with Neptune, so Uranus gains speed. But as it overtakes Neptune, Uranus slows down. By taking these disturbances into account, astronomers find Neptune. Neptune on the left is denser but slightly smaller than Uranus. Our planet would stretch across Neptune more than 4 times, a width of just under 50,000 kilometers. To span Jupiter, 12 Earths or 3 Neptunes more than do the job. After the blur of Uranus, Voyager sees plenty of weather. Here, a cloud whips through the upper atmosphere. Neptune is the windiest place. At the equator, gales roar at 2,000 kilometers an hour. These cloud tops are cold, minus 200 degrees. But the weather is driven by internal heat, something missing on Uranus. Voyager tracks a tempest the size of Earth, the Great Dark Spot. Over a number of days, it changes shape. Although the spot hurtles around the planet, this Voyager time-lapse holds its center of frame. To the southeast, another storm, the Wizard's Eye, bigger than any typhoon on Earth. 7 years later, through the Hubble Space Telescope, the Great Dark Spot is gone. Neptune spins once in 16 hours. The atmosphere is 85% hydrogen, 12% helium, the rest mainly methane. There are 4 distinct layers. The outermost is stratospheric haze with lots of hydrocarbons. Lower down, hydrogen and methane. Then ammonia and hydrogen sulfide, and a transition zone of gas and liquid. Toward the center, liquid hydrogen. A mantle of ices. And a rocky core. Neptune has two main rings, parts of the outer ring thickened where material has clumped. In imaginary close-up, particles of icy dust. There are 8 confirmed moons, 6 discovered by Voyager, all tiny except one. It is Triton. 2,700 kilometers across, Triton has the coldest known surface, minus 238 degrees. Yet it spurts blackened nitrogen. These geysers shoot 8 kilometers high, their plumes carried downwind in the wispy atmosphere. Triton may be a captured planetesimal, like Pluto, the planet beyond, a world at the very edge. The Lowell Observatory, Flagstaff, Arizona. In 1930, the outermost planet Pluto is discovered through this telescope. Astronomer Clyde Tombaugh makes the find. He's 24 at the time. Tombaugh does it by systematically photographing the sky on large glass plates. He snaps each piece of sky twice, several nights apart. Then, with this blinker, he compares the two images. If they're identical and nothing jumps, he's not interested, for only objects within the solar system move against the background stars. After 6 months of blinking, the dot that jumps is Pluto. Pluto and its moon Charon have a combined mass of less than 1/5 of our moon. Little frontier worlds of methane and water frozen in the outer gloom. On average, compared to Earth, they're 40 times farther from the Sun. Far beyond is the Oort cloud, a swarm of freezing debris that shrouds the solar system like a sphere. Closer in is more icy trash, the Kuiper belt. Pluto, with its wide, eccentric orbit, may well be a member of this belt and not a true planet. Like the comets that visit us from Kuiper and Oort, Pluto is a mixture of ices. This is Comet Hyakutake in 1996. Its nucleus is a snowball 3 kilometers wide, but the tail stretches for millions of kilometers. As a comet nears the Sun, it grows 2 tails. The yellow one is fine dust, the blue, gas. The gas tail detaches occasionally in the gusting solar wind. It's that wind, plus the pressure of solar radiation, that blows the tails away from the Sun. With the solar disk masked, time-lapse of a comet rounding the Sun. Here, comets plunging into the Sun. Comets are the vagabonds of the solar system. Some travel on random elliptical orbits, hurtling among the planets. Kamikaze comets die in the Sun. Others just graze it. Jupiter plays havoc with comets. This one is captured from its orbit around the Sun by the pull of the giant planet. The comet, a fragile mix of ice and grit, is drawn within 50,000 kilometers. It pays the price. Jupiter tears it into more than 20 fragments, and it's just the beginning. The comet, named Shoemaker-Levy 9, is to stage the celestial show of the century. It's to plunge into Jupiter, carpet bombing the soupy atmosphere. The date, July 1994. The fragments create shockwaves as big as Earth. The moment of an impact. Lower left, a plume shoots over 1,000 kilometers high. The most famous comet is Halley. It visits our skies once every 76 years. When he sees it in 1301, the Italian painter Giotto makes Halley his Star of Bethlehem. The Bayeux Tapestry depicts the Norman conquest of England in 1066. The comet is overhead. On Halley's last visit, the first of the space age, we visit it. A craft aptly named Giotto is launched by the Europeans. It's the most ambitious of an international armada. For Giotto is to fly right through the inner coma, the cloud that surrounds the nucleus. It's 1986, and there is the nucleus, shaped like a peanut, 16 kilometers by 9. Vaporized by the heat of the sun, gas and dust vent from cracks in the surface. Glare obscures the view, but Halley's crust is carbon black. The coma, fed by the jets, is well over 1 million kilometers across, bigger even than the sun. These are the icy planetesimals of the Kuiper belt, a disk of debris just beyond the planets. It's from here that Halley originates, dislodged perhaps by a twitch in the gravitational interplay between the sun and its neighboring stars. Halley is lucky. As solar gravity draws it inward, the comet swings round the sun rather than into the sun. But Halley is now captive, trapped in an orbit that takes it out beyond Neptune, then back to the sun, again and again. Halley has an orbit of 76 years. Longer period comets arrive from farther out, comets like Hale-Bopp, the most spectacular of the late 20th century. (1997) is the year of Hale-Bopp. Here in close-up, the spinning nucleus, 40 kilometers wide, swirling gas and dust. They stream from the hemisphere heated by the sun, switching on and off as the nucleus rotates. At its closest to the sun, Hale-Bopp sheds 1,000 tons of dust every second. But in the chill of the outer solar system, comets revert to type. They become tailless and inert. Historically, comets always have tails, and they're linked to death and destruction. But fear of comets isn't all nonsense. To this day, they are cause for concern. Had Hale-Bopp struck Earth, we'd all be dead. But that's another story. The spacecraft Stardust on a close encounter with comet Wild 2. Like sticky flypaper, this instrument is to collect samples. as stardust travels through the coma of the comet. But unlike Giotto, which relayed only data from Halley, Stardust is to send its samples home. Insulated in a capsule, resistant to a fiery re-entry through Earth's atmosphere, a precious package from beyond the planets. Retrieved from a soft landing in the polar wastes, these samples of Wild 2 will be unique. The first chance for scientists to examine particles unchanged since the formation of the solar system. The Oort cloud stretches a third of the way to the nearest star. Its messengers are comets.